Yo, what is up, guys? Welcome back. Episode 87. So I talked about yesterday I was going to do a programming contest yesterday on Leetcode. That didn't end up happening. I ended up playing some Minecraft with some old friends from college. They wanted to play, so I thought I'd join in, I guess. So yeah. So I thought we could maybe go through some of the problems, and see if we could have solved them. And yeah, maybe we'll take a look at the first, maybe we'll look at each problem, just maybe kind of think about the intuition, probably if I could have solved it or not. But yeah, so we'll get into it. So let's do our Pokemon sound of the day. So episode 87, we have a Dugong Pokemon sound. Let's take a listen. Dugong gong gong. 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 Alright, last one. Dugong gong gong. There we go. Yeah. So let's take a look. This is our contest yesterday, April 5th. Today's April 6th. So let's take a look. Given array nums, you can perform the following operations any number of times. Select the adjacent pair with the minimum sum in nums. If multiple pairs such exist, choose the leftmost one. Replace the pair with their sum. Okay. So we're given 5, 2, 3, 1. The pair 3, 1 has a minimum sum 4. After replacement, nums 5, 2, 4. The pair 2, 4 has a minimum sum of 6. After replacement, right now is okay. So my intuition here, turn the minimum number of operations needed to make the array non-decreasing. Oh, okay. Right, I understand. So the pair 3, 1 has the minimum, right? After replacement, nums is equal to 5, 2, 4. Okay. The pair 2, 4 has a minimum sum of 6. After replacement, it's 5, 6. The array nums has become non-decreasing in 2 operations. So we would return 2. Okay. So I'm trying to think here. Well, my intuition here. My first thing I was thinking about doing was doing an n squared solution, the brute force solution. Maybe a double for loop, looping over each minimum number. This is an easy problem too. Interesting. Select the adjacent pair with the minimum sum in nums. Looking for the adjacent pair. Okay, well, if we were to split this problem up to different, the pair 3, 1 has a minimum sum of 4. Okay. I think we've done this problem before. But honestly, my intuition is in there. I'm not sure kind of how we would solve this. Turn the minimum number of operations needed to make the array non-decreasing. Thinking of doing a double for loop maybe with a while, but I just don't think that that's the right way to do this. I feel like there's an easier way. Check if I have solved this. I'm curious. I'm pretty confident I have solved this. I think I remember solving this. Pair removal, sort rate 1. I have not solved this. Interesting. I have not solved this problem. Maybe. I'm thinking, can we sort the array? Because then we would know. But is sorting the array really going to get us? No, it won't, because we need to take the minimum sum. So no, we can't sort. I'm thinking a double for, like a... We got to find the sum, right? To find the sum, we need 2 separate for loops, or we can... Okay, right. So we do 2 separate for loops for I in range length nums. Okay. For j in range length nums. We have to be 1 step ahead of j. So then we want to calculate our mid. So min is equal to oh my gosh, dude. So let's do our sum, or is it minus? Min sum. Min sum is equal to I nums I plus nums j, right? You want to do min sum? Oh, sorry, no. We just want to do cosum. Min sum is equal to max cosum. Sorry, min sum cosum, right? And let's print our min sum. Ah, jeez. Sorry, we need min here. Here's, yeah, 2. Okay. Right, so in this case here, we would go 5, 2, 3, 2, 3, 5. Sorry, 5, 2, 7, 2, 3, 5. 314. Oh, we want the minimum sum. How are we getting 2 then? 5 2. 5 2. 7. Then we would go 2 3 5. 3 1 4. How are we getting 2? Isn't this funny? Yeah, min sum, dude. Okay. Oh, we want cosum. Print. Whoops. Okay, we got 7. All right, then we move forward. How are we getting 8? Ah, okay, we're going 5 plus 3, but we only want adjacent numbers, right? So, oh my god, how did I not realize that? Yeah, that the for is looping like that. I think we can use a while then. Yeah, no, we can just get rid of that, right? We can do it with a 1 4, right? We can move through, and we can just get. You can just calculate I plus 1. Is out of range. Okay, we get 4 now. Okay, good. Okay. So we have 4. Okay. Thinking, how can we do this? Well, we can do okay, so maybe if we do this min sum, right, we can create maybe some sort of, we can create our I, our J, right, and then our I val, J val. I don't know if we'll need all these variables, right, but we can make okay, we can do it inside this if statement. We can do, well, if cur sum is less than min sum, all right, then we can make, well, I is equal to I, J is equal to I plus 1, I val is equal to nums I, and then J val is equal to nums J. Get rid of this. And then we make min sum is equal to cur sum. Let's run this code. We have to make this cur I. Cur J. Invalid syntax. Why are we getting an invalid syntax? Why are we getting invalid syntax, bro? What the hell? Oh my gosh, dude. Let's make this all 0. I mean, it doesn't really matter what it is, right? Because we're going to replace it. nums I plus 1. Okay, right. So now we do while outside of this while, okay, inside of this while we do while we're gonna need to sort somewhere down here, right? So like do nums2 is equal to nums dot sort, right? Nums2 is equal to nums dot sort. So we do, well, while nums does not equal nums2, nums2 is equal to nums2 dot sort. But now we need to actually remove the values, right? So we would do, well, nums dot remove. I remove value from array in Python. Is it remove? Don't remove, okay. Can you give the index? If you want to remove a value at a specific position, remove value, okay. We'll do delete nums cur delete nums cur j, okay. Right. Then we have to append our value, right? So we'd probably have to put it I think we have to delete cur. We don't have to delete j, right? We just replace, well, we make nums cur equal to min sum. Then we delete j. Then we sort it again. Then we check in this loop, right? We'd count 1, right? We'd sort, and then we'd want to make a count variable, right? Because we need to count the number of operations, right? So then we do, well, count plus equal to 1. And then I believe we would return count. Let's see if this works. Oh, list assignment index is out of range. Delete nums cur j. This assignment index is out of range. How is it out of range? Why am I getting list assignment index Out of range. I am not sure. Okay. Well, nums1 does not equal sorted nums, so that's a better way to do it. Okay, nums.sort is actually makes it in place, so let's remove that. For I, right, we do it. Okay, apparently we don't need this stuff, right? So let's get rid of this. Let's get rid of this. All right. Don't need this. We return the count. Num is not defined. Oh. Time error. Coj is not defined. Did you mean theoryyy? Lead nums I plus 1. I guess we could do theoryyy plus 1. Technically. I don't know. Maybe we have to put it inside the while. I think our count's fucked up. We're resetting our count here. We only want. I want 7. Expected 10. Yeah, I'm not sure. Not sure. What's wrong? It's probably something small, dude. Min sum is never reset. Okay, I don't think this needs to be here. I think this can be out here. Okay, we did it. That was a tough problem, man. It took me 30 minutes to solve it. Okay. Okay, so we could do one problem. Let's go. Alright, back to contest. We solved one. Design a data structure that can efficiently manage data packets in a network router. Each data packet consists of the following attributes. Man, I don't like these sort of problems. Alright, we'll leave it for that for now. Let's jump back to our actual problems that we want to do. Let's check out this one. Evaluate division. Okay, you're given an array of variable pairs, equations, and an array of real numbers values, where equations I is equal to A1, B1, and values I represent the equation A1 over B1 values I. Okay. Each A1 or B1 is a string that represents a single variable. You're also given some queries where queries J is equal to CJ DJ. It represents a jth query where you must find the answer for CJ DJ. Okay. I'm a little confused. There's a lot of information in this problem. Do you recognize this as a graph problem? I'm a little confused with the problem. There's a lot of information in this problem. Yeah, man. I am not sure. I don't even know how everything relates, to be honest. I generally don't even know how it all relates, like return the air. Ow. Let's take a look at the video because
I just discovered.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, evaluate division. I don't know if I'm getting dumber or these Leetcode problem descriptions are getting a lot worse. Well, I guess this is one of the early problems, but I'm just going to skip straight to the example because it's a lot easier to understand it that way. We're given a list of equations where the equations could be given like this, and keep in mind that these are strings, so A and B are going to be strings, and what one of these subarrays represents is A divided by B. So that's that's what this equation is. This equation is similar, b divided by c. So every equation is going to be in this form with some numerator and some denominator. We're also given a second array of the same size, which actually tells us the result of each of these equations. So in this case, a divided by b, we can see down here, it's kind of hard to tell, but the value is going to be 2, so a divided by b is going to be 2. B divided by c is going to be 3. Cool. Now, we are also given a list of queries, so that's what green is going to represent. And those queries are going to be in a similar shape as the equation, so it's going to be a sublist. In this case, one of the queries is going to be a, c. So what we want is to know the result of a divided by c. Now, it's not necessarily going to be true that we'll be able to determine it. And if we can't determine it, we have to put a -1 as the result. But if we can determine it, then we have to put the value of this equation, like what it evaluates to. And then we have to build a output array. So for each one of these queries, we'd have some output value. Now, in this case, a divided by c, can we determine it? Well, let's not even think about code for a second. Let's just try to look at like the math. Hopefully your algebra skills are good enough to be able to evaluate this. A divided by b is equal to 2, and b divided by c is equal to 3. Well, take a look. We can kind of multiply these two together, and the b over here is going to cancel out the b over here, and then we're going to end up with a divided by c, and multiplying 2 and 3 together, like that's the value of these two equations. So 2 times 3 is going to be 6. So we were able to determine it this time. I have no idea how we would code that up yet, but we were able to get the result of this query, which is 6. And that's what they have in the output as well. Now, a quick edge case worth mentioning is, what if some of these equations or the queries, like something like this, a divided by e? Well, we weren't even given an e character in the input, so it's definitely not possible to evaluate this. So for sure, we would put a -1 in the output, and that's what they do for this one. It's over here. Another edge case, and this one I think is kind of dumb. I really don't understand this. Take a look at this over here, x. So we don't know what x is. That's perfectly fine, but x divided by x should probably be 1, right? Unless we have some kind of divide by 0, which I believe they mention will never really be the case, and we won't have any contradiction, so we don't have to worry about that, thankfully. You would think this would evaluate to +1, but I guess in this case it doesn't. Over here, x divided by x gets us a -1. You can't really see it anymore, but it does give you a -1, or at least that's the expected result. That's kind of stupid in my opinion, but okay, we just have to account for that. The first thing I personally tried was, maybe we can just solve for every single variable, and then it'll be pretty easy to know the result of every query, because they literally are just a divided by some other variable. That's the form of every single query. My math skills are sharp enough to recognize that we actually can't do that in this case. We have, in this case, 2 equations, but we have 3 variables, a, b, c. So we simply do not have enough equations, unique equations, to be able to determine the value of a and b. It's ambiguous, and if you don't believe me, let me prove it to you. Let's just say hypothetically the value of a is 2. Then what must be the value of b to get an output of 2? Probably 1. Okay, let's say a is 2, b is 1. Okay, then we get a 1 over here. Then what's going to be the value of c? Probably a fraction, in this case 1/3. 1 divided by 1/3 is going to give us 3 in the output. This is one way of solving this equation. You can tell this math definitely works out. But now let me change it up. Let me transform a over here to now be a 4, and transform this to be a 2, and so that means it's a 2 over here as well, and then that means for this to equal 3, we have to make this 2/3. This is another way that the equations do work out. So what you find is we can't actually determine the value of each variable. And clearly this is a very simple example, but we could have had a ton more equations. And at this point, if I gave you this problem in an interview, I would definitely expect you to need a hint, because it's not very intuitive how to solve this problem, but actually it turns out we can transform these equations in a graph representation, which will allow us to solve this problem. Notice how when we have a query like a divided by c, we start with whatever we can. We start with maybe a divided by b. And at this point, we need a way to cancel this b. So we would look for all the other spots in our list of equations where b is in the numerator spot, because then we can get a fraction in this form, something in the denominator, who cares, it's an x, but we can get something in this form where we cancel out like this and we have a divided by x. We don't necessarily know we'll ever be able to figure out what a divided by c is, but this is our best bet. We have to sort of cancel out the denominator, because if we multiplied this by something else, like if I multiplied this by d divided by e, we're not getting any closer to this, are we? That's a little bit of the intuition. And also notice that when we do this, b divided by c, we are multiplying the values together. So this is a little bit of the intuition of why we want to map every single numerator to all of the possible denominators that it has in any of these list of equations. And it could have multiple, of course. In this case, our graph kind of looks like this shape. A points to B, B points to C. Now, it could have been possible that A, points to something else, like an X. In this case, though, our graph is pretty simple, so let's just try to understand this itself. Can I ask you, if we start at A and traverse the graph and end up getting to B, what does that represent? Doesn't that kind of look similar to this, like actually multiplying the equations together? This is kind of like A divided by B, this is B divided by C. And what we were doing with these values is trying to multiply them, so wouldn't it be kind of good to put the edges as the value of each equation? So A divided by B is equal to 2, B divided by C is equal to 3. Then the way we formulated the problem, a path from A to C, multiplying all of the edges together, must mean that A divided by C is equal to the multiplication of the edges. It's equal to 6 because of the way that we formulated it. I know this is kind of a crazy idea that really isn't common in data structures and algorithms. You probably haven't seen it before, so it might take you a second to really understand it, but it's
I was a little
in
confused.
the numerator spot, because then we can get a fraction in this form. Equations do work out. So what you find is we can't actually determine the value of each variable. And clearly this is a very simple example, but we could have had a ton more equations. And at this point, if I gave you this problem in an interview, I would definitely expect you to need a hint, because it's not very intuitive how to solve this problem, but actually it turns out we can transform these equations in a graph representation, which will allow us to solve this problem. Notice how when we have a query like A divided by C, we start with whatever we can. We start with maybe A divided by B. And at this point, we need a way to cancel this B. So we would look for all the other spots in our list of equations where b is in the numerator spot, because then we can get a fraction in this form, something in the denominator, who cares, it's an x, but we can get something in this form where we cancel out like this and we have a divided by x. We don't necessarily know we'll ever be able to figure out what a divided by c is, but this is our best bet. We have to sort of cancel out the denominator, because if we multiplied this by something else, like if I multiplied this by d divided by e, we're not getting any closer to this, are we? That's a little bit of the intuition. And also notice that when we do this, b divided by c, we are multiplying the values together. So this is a little bit of the intuition of why we want to map every single numerator to all of the possible denominators that it has in any of these list of equations. And it could have multiple, of course. In this case, our graph kind of looks like this shape. A points to B, B points to C. Now, it could have been possible that A, points to something else, like an X. In this case, though, our graph is pretty simple, so let's just try to understand this itself. Can I ask you, if we start at A and traverse the graph and end up getting to B, what does that represent? Doesn't that kind of look similar to this, like actually multiplying the equations together? This is kind of like A divided by B, this is B divided by C. And what we were doing with these values is trying to multiply them, so wouldn't it be kind of good to put the edges as the value of each equation? So A divided by B is equal to 2, b divided by c is equal to 3. Then the way we formulated the problem, a path from from A to C, multiplying all of the edges together must mean that A divided by C is equal to the multiplication of the edges. It's equal to 6 because of the way that we formulated it. I know this is kind of a crazy idea that really isn't common in data structures and algorithms. You probably haven't seen it before, so it might take you a second to really understand it, but it's pretty simple what's actually going on here. Now, another question you might have is, what if we are going in reverse order? C going to B, going to A. Like, that's a perfectly valid query. What if they instead ask C divided by A? Well, the way I formulated this was a little bit naive. Now we kind of realize numerators point to denominators, sure, but shouldn't denominators also point to the numerators as well? Can't we kind of do this in reverse order? Can't I also say this equation, C divided by B, which is, the reverse of this, multiplied by B divided by A, which is the reverse of this, isn't that perfectly valid as well? That gives us C divided by A. Yeah, I don't see any reason we can't do that, but if we try to multiply the edges going in reverse order, we still end up with 6. So how can it be possible that A divided by C equals 6 and C divided by A equals 6? I'm pretty sure that's a contradiction, and it is, and that's when you realize when we go in the reverse direction, we should take the inverse of these values, because that's exactly what these are. These are the inverses of each other. If you don't remember what an inverse is, it's basically 1 divided by this number. So what we essentially learned here is that our graph is going to be directed. The edge going in this direction is not going to have the same weight as the edge going in the other direction. This one will have a weight of 1 divided by 3, and this one will have a weight of 1 divided by 2. So this is basically how you need to formulate the problem in order to solve it. Is it intuitive? Not for me, but I hope it's starting to make sense for you. And I'm a big math fan, so I thought this was one of my favorite problems I ever solved. Okay, so knowing all of that, how are we actually going to solve the problem? Well, first we're of course going to have to build this graph, essentially just building an adjacency list using these as our edges, and we are given the values as well. Those are going to be the weights of each edge, and we're going to build like the reverse edges as well. And then for every single query, we are kind of going to do it a brute force approach, which thankfully is good enough for this problem because it is a medium, so I think that should be perfectly fine. And by brute force, I mean on the graph for every single query, we're either going to run a depth first search or a breadth first search, so potentially traversing the entire graph. I believe the time complexity is going to be n for the number of queries multiplied by the size of the graph, which I believe is e plus v, where edges plus vertices. To simplify this, I think just having e for like the length of the equations is probably sufficient, n times e, where this the number of queries. Space complexity should just be the size of the graph, which is going to be v plus e. So now let's go ahead and code this up. Like I said, first step is going to be building the graph. In Python, what I'm going to do is create a hash map collections.defaultDict, where the default value is going to be a list, because what we know is we're going to map every numerator, or just every number a, such that it's mapped to a list of pairs, where each pair is going to be b, where b is just a variable, and the second value is going to be the evaluation of a divided by b. If this doesn't make sense, don't worry, it'll probably make sense as I actually build this. So what we're going to do is iterate through every equation, but in Python, we can do it like this. For I equation in enumerate the list of equations, reason I'm using enumerate is we not only get the value from equations, which is here, but we also get the index as well, which just saves saves us a little bit of boilerplate, and then we can unpack the variables from the equation because we do know it's a pair of variables. We know we want to build directed edges, so from A, we're going to append the neighbor B, and what is the evaluation of A divided by B? Well, thankfully, that's going to be stored in values at index I. You can see why we needed the index I now. And we also know we want to do the same thing going in the opposite direction. So we might just say B divided by A, but there's a bug, remember? It's not going to have the exact same weight, so we want to take the inverse of this, so we say 1 divided by that. In Python, 1/ means decimal division, which is exactly what we want in this case. If you're using like Java, I think that'll be integer division, so you want to keep that in mind. But next, we just want to run every query and get the result of it. We can do that with a DFS or a BFS. I'm going to do BFS. The main reason is it's easier to handle cycle detection, and it's possible that our graph could have a cycle. So BFS just makes it a little bit easier for us. What I'm going to be passing into our BFS is going to be the source and the target. And what that's going to be in this case is if we were given a query like A divided by B, then the source is A, and we want to find a path starting from A, getting to B. And once we get to B, we just want to multiply the weight of all those edges and return that. So that's what this is going to be doing. So before I even implement it, I like to show you how I'm actually going to be using this. So for every query in our list of queries, we want to call BFS, passing in Q at index 0 as the source and Q at index 1 as the target. And we can use this to build an array, but in Python we have a nicer syntax called list comprehension. So we can build a list just like this by putting a for loop inside of it. So for every query, this is the value that we want to add to the list, and it will execute in order as well. So this is the result that we're going to end up returning, and now all we have to do is actually implement the BFS. And before I forget, I want to say that remember, if any of the source or the destination is not in our list of equations, which means it's not in the adjacency list, then we want to return -1 immediately, even if we're given something where the source and the target are equal. Like I said, I think that's kind of weird. X divided by X should always be 1, but in this case, they want it to be -1, I guess. So if source is not in the adjacency list or target is not in the adjacency list, we return -1. Now we have our pretty cookie cutter breadth first search where we're going to need a queue and a hash set, and I'm going to use a deck and a hash set like this. We initialize our queue just starting at the source, but I'm actually going to also add a second value because remember, we do want to keep track of the multiplication of all the edges. But since we're not doing this in like a depth first search way where we might go to A to B to C, etc., we're doing it layer by layer. We could start at A, and then the next layer could be something like A and D, and then the next layer could be something like C and E. So we want to simultaneously keep track of the multiplication of these edges and these edges. So instead of having a bunch of variables to do that, we can just use the queue itself. Every time we add a value from our graph to the queue, we're not just going to add the value, we're going to add the total multiplication of the edges so far. What do you think would be a good starting value for our source node to have for the multiplication? Probably just 1 because it's a neutral value. Any value multiplied by 1 will end up being that value. And I also like to immediately add to the hash set the source node. And then we want to do a BFS. So while the queue is not empty, we want to pop from the queue. We're going to append to the right, so we want to pop from the left. And when we pop, we end up getting the node and the weight. I'm going to store that in N for node, W for the weight. And you might think, let's immediately just start going through the neighbors in the adjacency list of the node N. But remember, before we do that, we're looking for the target. If we find the target, there's no point in continuing. We're not doing this for fun. We're looking for the target. So if we get to a point where N is equal to the target, then we can go ahead and return. What should we return? Weren't we trying to multiply all of the weights? Well, yeah, but remember, when we append to the queue, we're going to be appending the multiplication up until this node. So W is already the value we want to return. So just go ahead and return it here. Okay, we have that handled, and we know actually this might not always execute. So to be safe, Let's put a -1 over here. It's possible that both the nodes exist in the graph, but there just happens to not be a path connecting them. In that case, we would return -1. But now as we go through every neighbor of this node, we remember that we're not just going through the neighbor, we're going through the pair, which is the neighbor and the weight. So the second parameter is going to be weight. Well, not parameter, it's a variable. And I know this can be slightly confusing because we have two variables referring to the weight. But now for this neighbor, we want to traverse the BFS from this node as well, but only if it's not been visited. So we say for neighbor not in visit, if neighbor is not in visit, then we can go ahead and append to the queue this neighbor and the new weight.
Oh man, this is a little confusing. Not gonna lie. I do want to look at something though.
How do we get the weight? Do we just add the weight of this node? That's not enough because that's only the weight connecting A and B. Do we just add the W value? Nope, that's only the multiplication of the nodes before we reached this node. We actually want to multiply them together, W times weight. And we also, before we forget, want to make sure this node is marked visited. So I believe that is the entire code. Let me go ahead and run this to make sure that it works. Okay, it's always the simplest things you mess up on. I think I forgot to add dict over here. This is a default dict. And also when I append to a list, we're appending a pair, but here I didn't really do that. So I want to wrap this in a list and this one as well. Okay, now let's run this to make sure that it works. And as you can see, yes, it does, and it's pretty efficient. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out neetcode.io.
See if I can understand this code. Let's keep going through. Let's just write it, right? So what does he do here? I'm gonna put this over here. So we build our JSON list, right? So he maps A to the list of B, A divided by B. Dot default dictionary list. Okay. For I, an equation in enumerate equations, right? Because equation, and then we have the values, right? So this equation here maps to this value. This equation here maps to this value. Okay, right? A, B is equal to equation. I think I know what this is going to print, but I just want to make sure. What type error? None is not valid. Okay, it'll be fine. AB is equal to equation. Dot append B values I. One of the values I. Okay, let's print our JSON list. Do I need it for this one too? You mean a valid return type, bro? Like, this is gonna get an error now. Bro, what the That's why I sometimes hate Leetcode, that it doesn't let you visualize stuff. I'm such a visual learner that, like, indentation error, dude. What the fuck? Default. I have to go to the bathroom, dude. Okay. I'm gonna leave it. I'm gonna go to the bathroom. I have to go to the bathroom so bad. We need this here. Be back in a second. A, B, C. Where pen values I. Okay. So we got to visualize it. So now let's look back at the thing, right? So we now perform our BFS, right? So we would do def BFS, pass in our source and our target, right? Okay. So let's check out our queries thing. AC, BCA, AE, XX. Okay. I'm going to do the return statement here. So we want to return. Doing list comprehension here. We want Q0, BFS, Q0, Q0, Q1 for Q in queries, right? AC. So Q0, Q1. So we're passing in this as our source, and then CB is our target. Okay, let's get our queries here. Oh, Q0, Q1 for Q in queries. Okay. That's right, I didn't see it. Okay, so for Q in queries, we have Q0, Q1. Okay, and that is A and C in this case, right? Okay, so now we take a look. Well, if source not in AGJ and target not in AGJ, you return -1, right? Okay, so if we right? So if E's in there, we return -1. Okay, that's simple. And if X is in there, this is, we're looking at the first example, example 1, right? If we have E, we're obviously going to return -1 because it's not in there. If we have X, we return -1. So if it's not in our initial thing, we return -1. I understand that. Okay. Now, we want to apply our BFS here, right? So we create a queue, right? So Q is equal to DQ. Alright, and then we want to create a visited set. Visited is equal to set, right? I want to come up here from collections, import DQ. Okay. Now we want to append our first value, right? So q.append source 1. Alright, but why do we append 1? I'm pretty sure he mentioned that in the video. Why do we append 1? We append 1 because 1 doesn't affect anything, right? One is our weight, right? So we append our weight. And then we add it to our visited set. So visited dot add src, right? We loop through our queue. Okay, we pop obviously from our queue, so we would pop our, I guess, our node and our weight, right, is equal to q.pop left. Okay. When we pop, we check, well, if node is equal to target, we just want to return our weight. And then we loop through our neighbors for neighbor and the weight in the adjacency list, right? Our node n. Okay. Let's do weight 2. Okay, an adjacency node, right? If neighbor not in visited, q.append neighbor and weight times weight 2. Then we add it to our visited.add neighbor. And then we return -1 if you can't find anything. Okay. So I'm thinking we understand this. This is definitely hard to think, but one thing we did learn is we learned how to use weights, right? And how to calculate the weights. I feel like now I just kind of have to loop through kind of what we're looking at, right? So let's say we're in queries, right? We're looking for AC, right? So we pass an AC into our BFS, right? We check, well, if SC not an AJ and target not an AJ, we return -1. Okay, so, well, it's not. They're both in there, so we skip this part, right? I don't know why this is not submitting. Oh. Missing something. -1. Why are we not getting it? What are we missing here? I am not sure why we're not turning -1, -1. That's been -1.0? No way, bro. No way, this is the reason, like. Bro, what the fuck is going on right now? Node wake, Guido pop left. Bro, what? Bro, what is going on right now? Bro, I am so confused right now. Generally, like, so confused. Where are we adding a 1? We're not adding a 1 anywhere. What the fuck was wrong? Like, oh, I think our return statement. No? I think it was like the return statements that were messed up or something. They added this line here. I think it was my indentation. I'm gonna go with that, but anyway. Let's walk through. Okay. So if we were to pass in our first one, AC, right? We're gonna go through our BFS. If SC not in, okay, that's not true. We create our queue. We append SRC, which in our case is A. We append it with the weight 1.0, right? We add A to visited. While queue, node weight, we pop, right? If node is equal to target, which it's not, right, then we look through the neighbors, right? And the neighbors here, we have B, right? So we go for neighbors, edge weight, and blah, blah, blah. If neighbor not visited, which is not visited, then we append to our queue, right? So we would append B. We'd append our current weight to our edge weight. Our current weight, yeah, to our edge weight, right? We do 1.0 times 2.0, right? So we at 2.0 right now, okay? Then we go, we loop through again with our queue, right? Because we look in our neighbor now, so we'd pop our neighbor, which should be B and then 2.0. Okay, well, it's not equal to that, so we go through the neighbors now, right? So we go through A. We said A isn't visited, so it doesn't go into this. Then we go into C, and we see, well, C is not a visit, so we append Q and we add the weight, which would be 6.0, right? Then we go through the Q again, we pop. We see the node is equal to the target, right? And then we would just return that weight, so we return 6.0, right? And you can see here, that's our first 6. Okay. Then we go, we return our weight, right? So we return BFS Q0, Q1 for Q in queries. Okay. Definitely was a tough problem to think about. I think the hardest part about this problem was one, understanding kind of how everything links. Let's go through our next one here though really quickly. We'll do BA because that goes the opposite way. So let's take a look here, right? So we go, okay, well, what's BA, right? So if SRC not an AJ, target not an AJ, we return 1.0. We have our queue. We have our visited. we append our source, right? You know, our source in this case is B, right? So we add B as visitor, then we add our Q, we pop our weight, right? And we check, well, okay, B is 1.0, right? So then we would loop through for neighbor and edge weight, right? If A not unvisited, okay, so A is not unvisited, so we append A, we go through A, we add the weight, so we do 1.0 times 0.5, right? So we'd be looking for we'd have 0.5, yeah, because then we're at A now. We see A is equal to target. We return A. Okay, interesting. I understand how the problem's working. I understand the BFS. I understand pretty much everything. I just think the tough part was just understanding in the beginning, like kind of how it all correlated and how like the division and all that. Like, I feel like if it was a little bit more of a graphy problem, you know, you could kind of get that intuition right away, like what to do. Probably been easier to solve, but overall it was a good problem, and that probably took us like an hour to go over. Yep, it did. Anyway, let's take a look at some other stuff. Let's grab some more graph problems, right? So let's check out like let's finish that last easy that we were going to look at, the graph. Find if path exists. Okay, this is a bidirectional graph with n vertices where each vertex is 0 and -1 inclusive. The edges in the graph are represented as a 2D integer array of edges where edges I is equal to blah blah. Okay. You want to tell me if there's a valid path that exists from vertex source to vertex destination. Okay. So given a source, we're given a destination. And we just need to return true if there's a path, right? Oh yeah, and this is a very, very simple graph problem. There's 61 online in this question. So let's build our adjacency list, right? We can pass in our edges, okay? So let's do adjacency list. Let's do graph is equal to adjacency list. We pass in our edges, right? Inside of here, we want to loop through, well, for I in edges, right? We want to get AB is equal to I, right? If A not in, oh, we create a graph here, right? Little dictionary. If A not in graph, then graph A is equal to this. If B not in graph, graph B is equal to this. And then we just want to append here. So we want to do, well, graph A, this is a undirected graph, so we want to append both, right? Graph B dot append A, okay? And then that should be good. We just want to return our graph, right? And let's print it, right? Print graph. Okay, for edge in edges, right, is equal to edge. I'm building it wrong here because we should have 0, 1, 1, 2, 2, 0. But we have kind of the opposite here, so what is going on here? I think we have something wrong over here. Graph A. Over a key error here. I don't know why this is not building. Oh my god, I've got it in the 4. That's why, bro. I'm so stupid, dude. Oh. I don't have this in the 4. There we go. Okay. Okay, 0, we got our edges 1 and 2. In 1, we got our edges 0 and 2. In 2, we got our edges 1 and 0. Now, this can be easily done. We're going to do both. Just this example, we're going to implement BFS, and then we'll implement the DFS solution, right? The DFS is a little bit harder to implement. It's a recursive solution, which is good. I think good practice, but we're going to implement the BFS solution first. So we'll do... let's do def BFS, right? We want to pass in our source and our destination, right? Okay. We get our graph, and we also want to pass in our graph to Loki. Okay, let's if BFS graph source destination equal to true, you return true, right? Else you just return false, right? Because we're only checking once, so really this is fine what we're doing here, alright? I guess, or we can honestly make this way better. We can just return BFS graph source destination. Okay, so in here we want to create a queue, right? So let's import our queue from collections, import DQ, right? We want to do, well, we want our queue is equal to DQ, right? We want to create a visited set, right, to avoid loops. You know, this could be a connected graph. So we would do, well, queue. Probably want to pass in first what we're going to look at. So we look at our source. I think really all we need is our source, to be honest. Source. While queue, right? And we pop, we do, let's do node is equal to queue.pop left, right? We check, well, if node is equal to the destination, then we want to pop, right? So if it's equal to destination, we want to just return true, right? Otherwise, if for neighbors in graph node, I check, well, if, let's do if neighbor not in visited, right? Then we want to, if neighbor not in visited, then we want to do, well, visited.add. No, let's append our queue. We do queue.append neighbor, right? Append neighbor, and then visited.add neighbor, right? As we get through all this, right, we would just, I guess we just want to return false, right? Unhashable type list. I don't know what that means. Why are we getting unhashable list? Unhashable list. What does that mean? Because you're mistakenly appending list neighbor instead of just neighbor. Oh, okay. Then I guess we don't have to do the same here, right? We're appending the list. Object is not iterable. Okay. Sweet. Okay. We're gonna do the DFS example, right? We're gonna implement DFS this time, so we can get a bit of both, right? Let's do DFS, right? So the way we would implement DFS is, how would we implement DFS? Okay. First, I think we do visitor.add, right? And we'd add our current integer that we're looking at, right? So we would add, SRC, right? Then we would want to check, well, if source is equal to the destination, right? We would then want to return true, okay? Then we'd want to loop through our nodes, right? For neighbor in graph source, we'd want to check, well, if neighbor not in visited ooh, shit. You need to create. I think we need to create a new visited array, visited set, and we'd have to pass it in. I think. Okay. We would add it to visited, we'd check out thing, we pass through our neighbor. If neighbor not in visited, we would call our DFS function on our neighbor. But this time we'd pass in graph neighbor destination visited, right? Once we get through that, we'd want to process our visited, right? So we want to do, well, union find. Okay, so we do, well, visited.remove neighbor. Oh, visited.remove source, sorry. Then we'd want to return false, right, if we don't get it true. Let's think about this, right? Let's open our paint. Let's think about the DFS recursion stack here, right? So we start off with our graph, right? Okay. What the hell is our graph? We start off with our adjacency list. Okay, I'm gonna draw it over here, right? We have 0, 1, 2, 3. Okay. Okay, so then we have 1, 0, 2, 1, 3. We have 2. Okay. We want to check. Let's draw our graph though, right? So we have, wait, why do we have a 3? We don't have a 3. What is going on here? We have 0, 2. So 0 connects to 1 and 2, right? One connects to 0 and 2. And then 2 connects to 0 and 1, right? This is what we got. This is what our graph looks like. Okay. 1, 2, and we have our visited set. I'm going to call this V, right? And this is going to be our values inside our visited set, okay? So we start off by adding our source node. So we start off by calling the source that we want to find, right? In this case, we have 0, okay? So we add 0 to our set, okay? Then we call, okay, if source is equal to destination. Well, our destination, okay, we're looking for 2. I'm going to put this in a different color, right? We're looking for 0. Sorry, that's our source. This is our destination, right? So we're looking for 0, right? So we first pass in our source. We add our source in here. Is source equal to destination? Well, no, it's not, right? So then we go into our neighbors, right? We see, well, okay, we look at, okay, 0, we have 1, right? So then for neighboring graph visited, if neighbor not in visited, then we call DFS 1 on it, right? So now we're at 1, okay? So now we're at 1, okay? And we check, well, the source equal our destination. No, it doesn't. We add 1 to our visited set, right? No, it doesn't. Then we would call, we go into our neighbors again. We call for 0, right? Well, 0 is not in visited. 0 is in visited, so we skip that. Then we look at 2, right? Then we add 2. Here we call 2, okay? We call 2, and we see, well, okay, our source is equal to destination, right? So we will return true, okay? Then we go back to our other function. Now DFS true is here. We'll come back here. We would remove visited, right? In this case, we came back to 1, so we remove visited, and we return false. Okay, so obviously that's wrong, right? And then we come back to this other call, 0, right? We called here. This would return false, right? So then we visited.remove. We remove this, and then we'd have 2 left in it, and we'd return a false call, right? Which is not what we want. Okay, we want to return true, 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 true. So then I guess if we come back here, we'd have to have some sort of condition here. I think that if DFS visited is equal to true, then we just want to return true. Will that work? Oh, there we go. Is that? Nope. Maybe it's not gonna work. Time limit exceeded. Why are we getting a time limit exceeded? We're stuck in some while loop here. Why are we getting a TLE? I don't know why we're getting it though. I don't think maybe we're not doing this properly. Okay, so maybe, so they're telling me that I need to move this up here. Remove this. They're telling me that this works. This removes a TLE. Really? Interesting. Okay. All right. So I think we didn't need that because of the type of problem, and I probably should have realized that because we're not going to need to keep looking for different directions, right? Because we're really only looking, does this source reach this destination, right? So, yeah, that's our problem. Anyway, that was a good problem. Okay. Let's see, how long have we been going for? Do we want to do a graph problem? I want to do one more problem, but I don't know. Should we do a graph or should we do the problem of the day? Given a set of distinct positive integer nubs, return the largest subset answer such that every pair. I don't want to do this question. Kind of want to do something else. Let's do another graph, man. I really want to do another graph. I'm starting to kind of understand it, and I want to keep pushing ahead with that. Yeah, let's search just in a tag. We'll search graph. Let's take a look at like a medium problem, and we'll sort it by acceptance. All paths from source to target. Okay. Okay, you're given an integer n denoting the number of cities in a country. These cities number from 0 to n-1. You're also given a 2D integer array roads, where roads I is equal to A1, B1 denotes that there exists a bidirectional road to cities A1 and B1. Okay. You need to assign each city with an integer value from 1 to n, where each value can only be used once. The importance of a road is then defined as the sum of the values of the two cities it connects. Return the maximum total importance of all the roads possible after assigning the values to them. So we're given an n value representing the nodes, and we're given the rows that connect, right? We have 0, 1, 1, 2, 2, 3, 0, 2, 1, 3, and then 2, 4. So this is a undirected graph. And to assign each city with the integer value from 1 to n. So what are we actually doing here? We want to denotes there exists a bidirectional road. So we need to output 43. The figure above it shows the country and the assigned values of 2, 4, 5, 3, 1. Road 0, 1 has a importance of 2 plus 4 is equal to 6. So 2 plus 4 is equal to 6. Okay. The road 1, 2 has an importance of 4 plus 5 is equal to 9. Consider which city contributes to the total importance of all roads based on that. I don't really understand how they're assigning this importance here. Okay, so I think it's maybe based on the number of edges, I think. So here we have 4, that's why we get a number of 5, right? And we have 3 over here, this gives us a 4. Then we have 3 here, which gives us 2, 2, and then 1. Okay. Let's see here, this is given 1, this is given 2, 3, and this is obviously 5, right? Otherwise, okay, well, it's like based off edges. So let's build the adjacency list, right? So let's define our adjacency list. We pass in our roads, right? For road in roads, right? Let's create our graph. Okay. We do AB, A comma B is equal to road, and if A not in graph, then graph A is equal to this. If B not in graph, then graph B is equal to this. Then we do graph A dot append B, and then graph B dot append A. We obviously want to return our graph, right? So and then we do, well, do graph is equal to ADJ list roads. Let's print our graph. So again, I think it's depending on the list, then we assign the value, right? Hmm. We need to somehow maybe create an array of some sort that denotes the importance. So maybe we can create an array that denotes 0 has an importance of Let's do, well, I understand. Okay, we did this. So now we need to, step 2, we create the importance depending on edges, right? So let's do importance is equal to this, right? For node in graph, if node graph node importance node is equal to the length of graph node. Okay, we got that. Now we want to sort the vertices by their degree in descending order. Sorted underscore vertices equal to sorted. Sorting. Function for sorting. I have to go to the bathroom again, bro. Jeez, man. key is equal to lambda item 1 reverse is equal to true. Which I believe this should. Let's print our perhaps you forgot a comma. I think there's a comma there. Okay. Step 4. Now we want to importance values. We are creating a new hash map here, assigning importance values. So for I, the vertex degree in enumerate sorted underscore vertices, right? We're doing importance vertex is equal to n minus I. Why? Let's print the importance. Okay, yeah, 5, 4, 3, 2, 1. Okay. Then step 5. Calculate importance. How would we do that? Well, we do for road and roads. A B is equal to road. Right, we would do, well, res plus or equal to importance A plus importance B. And we would just return our res. Take a plan D first. Interesting problem, bro. People get like so toxic on here, bro. Like, my solution is van, my solution is whatever. Like, bro. Like, come on. Array 0 times n for A, B, and rows. Array A plus equal to 1. Array B. I and range length of array sum plus or equal to array I times I plus 1. Alright, interesting solution. I'm going to call it there. I appreciate you guys watching. I will see you tomorrow.